not, you just use an embedded adders. It depends at what type of FPGA you are using. Number one, sometimes they don't have those many adders, and you may run out of them if you just let the synthesis tool use adders, even if you're adding 4-bit number or 8-bit number. So it does not really uh, optimize your design. So preferably, sometimes, like if you have smaller adder, and we will see that there are other like things, not only just adders. Um, Once you are adding many numbers, an adder tree, for example, so there are smarter ways of implementing an adder tree rather than just using physical adders. And in that case, you also need to know all these techniques. So one of a smarter way of adding numbers is called conditional sum adder. And this is kind of a carry select adder, but here the groups are made. I think we are still, yes. So groups are made on bit by bit basis. So in carry select adder, last time we saw we have a hierarchical carry select adder has group of 444, and then we combine group of these four together made a group of 888, then a group of 16 a bit together. So finally adding the numbers. So what a carry select adder does is that it just on a bit by bit basis, it has the groups, and every pair of bits you generate sum and carry at each bit position, assuming that carry in is 0 and carry in is 1. Okay. So, and then once you are done that, now you start combining these two together. And every time you pair up two pairs, two concatenated closer pairs together, make a bigger and bigger and bigger groups. So one pair assumes carry in 1, the other assumes carry in of 0. The correct sums and carries are then selected using a tree of multiplexers. This is working. So a tree of multiplexers, uh, and sum and carry of next bit position brought down to level 2 are selected by the least significant carry. And so this is just a description, but if I tell you this is once you assume that you are adding to number and carry is 0, and so its sum will be just XOR of the two. And if you are adding to number and you know the carry is the previous carry is 1, so it is like you are adding 1. You assume that carry is 1, and then you are adding two bits together, one bit, other bit. So this is the logic then. So this is the logic. And same is the case with carry. If you are assuming that the carry in is 0, and this is the carry if you assume uh, and carry in 1. So in this case, this is your sum 1, and the carry you generate is carry 1. So you have these 4 bits. So 2 bits in, 4 bits out, sum 0 carry 0, sum 1 carry 1. So you are adding every bit position with all these assumptions. So for example, these are the 3 bits that you are adding. So every bit you add, assuming carry in is 0. So if carry in is 0, you get 0 and 1. 0 sum, 1 carry. So you are writing here. Instead of writing it like this, you are writing like this. And similarly, 1 0, same. So 1 0 is assuming carry in of 0, you get 1 0. And here 1 1 is 1 1 0 1. You know, once you add 1 and 1, it is you get sum as 0 and carry as 1. So you write it here. And now add the same bits together, assuming uh, carry in is 1. So you get these 3 positions. Okay. Now you are going to merge. This is already 1 because so this is 3 bits. So you have these 2 together, and this is one you put it, keep it separate. Now you mix these two together. How you mix? You take the least significant carry, which is this, and resolve as if these two bits are added, assuming carry 0, so you will have this answer. And the same two bits are added, assuming carry in 1, you have this is the answer. These three bits are going to be the answer. And how you resolve it, you check this because this is 0. So you know if this coming from here, the carry is 0, your answer is going to be 1, 0 and 1 because this is 0. So answer is going to be 1, 0 and 1. So you drop this 1, 0 and 1. So merging will have these three bits. And then now you check this bit, and as it is 1, so you have if carry in from the back is 1, so this is your answer is going to be 0, 1, 0. Now you merge these two together and you check this carry. This carry is 1, so you select these three bits. If you have a 0 here, you would have selected these three bits. So that's how you get an answer. So very in few levels, in like few muxes, you can just get an answer of even this is an example of a 16-bit adder, as you can see. Usually the carry in of you assume carry in of an adder is 0, so that's why you have only this where you are adding assuming carry in of 0. But rest of every bit position you add these two bits together, assuming, let me take another color pen. Yellow should be fine. So these are the bit positions. So you add assuming carry in of 0, carry in of 1. You add these two bits, assuming carry in of 0, carry in of 1. Add this. So adding all these bits, assuming carry in 0 and carry in 1. So this is your first thing. Now you merge these two groups. These two groups are two bits together. So you merge two bits together. And how do you merge? Again, you look at this. If you have, let's say you have 1 here. So your first answer will be 0, 1, and 1. So this is your answer because if carry coming from the back is going to be a 1, then this is how you're going to merge. And this is what is shown here as well, 0, 1, 1. And as it is 1, the answer is going to be 1, 1, 1. So the answer is 1, 1, 1. Okay, so you check this carry. If it is 0, you pick the upper one. If it is 1, you pick the lower one. And that's how it's just a multiplexer. And so you pick. So now you have, I know this may again, if you understand it, it is good, but you have to really spend some time in just understanding that how this thing is happening. Now you are mixing, for example, these groups together. And how do you mix? If it is a 1, so here it is a 0, so you are going to select these. So your answer is going to 1, 1, 0, 0, 1. So 1, 1, 0, 0 sorry, it has merged these two groups. So it is 0 is 1, 1, 1, 0, 1, 1, 1, 0. And you have 1 here, so your answer is going to be 0, 0, 0, 1. So answer is going to be 0, 0, 0, 1. So again, once you are merging, you look at these bits. If bit is 0, you select the above answer. If it is 1, you select the lower answer. For example, here it is 1, so you are going to select the lower answer. So your answer is going to be 1, 1, 1, 0, 0, and then 0, 1, 0, 1. So 1, 1, 1, 0, 0, 0, 1, 0, 1, and the carry of this. And then you merge this, and finally. So again, if you go to ChatGPT and ask to generate me a conditional sum adder. So it will just generate an adder which you can then instantiate. So you see this is how the the muxing is happening, the merging is happening. So you have these multiplexers, and all these multiplexers are merging two of them together. So these and this are merged together, and similarly this and this are merged together. These are so series of multiplexers you merge, and 16 bits are added by spending. So it's again the trade-off is the same. The trade-off is uh, the same. Trade-off is that you throw more area, and you get faster adder. And if you have to pipeline it, so you can put a pipeline as well. We'll see how pipelines are done. Now, this is important, and this is why I covered all of this, that why first you would explore the design space, and definitely you can instantiate an already embedded adder if you are using an FPGA. But please remember, once you start consuming them, you may have only very few, so you end up consuming all of them. So you have to see that how many actual physical of these adders and multipliers are there on your device. For example, if you're implementing a CNN has so many requirement of so many addition and multiplication, and we'll look into those algorithms as well. So then you have to think, should we do that or not? So uh, so that's why you got to just uh, know that there are other options. So here is how I would write a test bench for this. So I have now asked ChatGPT to generate a code, which is a pretty complex code for a carry select adder. It's not a hierarchical carry select adder. I may ask it to develop a code for a hierarchical carry select adder. If it's a bigger adder, let's say it's a 32-bit adder or a 64-bit adder, or 128-bit adder or 256-bit adder. So I will ask it to have it this as a hierarchical carry select adder. And secondly, because you don't know what will match better on a CLB based FPGA. So we'll spend some time learning about how these FPGAs are. And so you may want to try, because it's so convenient to just generate an adder and definitely to see whether it's working fine or not. And this is how you write a stimulus. So one approach of stimulus is that you have a golden model, which in sometimes you have to buy it. Okay, so you got to spend money to get models, and these are usually models of standard interfaces like PCIX, and you want to have a model of the PCIX, which is a golden model, and you want you are developing your own on an SoC. So you got to have a model, or it's an algorithm. It's a CNN algorithm or any other type of algorithm which you have already implemented in C or Perl or Python or MATLAB. So you can just drop that in also. You say, oh, I have already spent a lot of time in validating the functional correctness of my software implementation, and all I'm doing is now that I'm implementing it in hardware. So I want to make sure that this functionally correct implementation can just be used in my stimulus in this fashion, that my the golden so in this fashion where I have a model. So I have this model, I have this device under the test. I use the same pattern, same test patterns. Okay. And I basically pass it to the device under the test, and I pass it to the golden model or my model as well. And then I have a way to do the comparison. And not only that, I also have a way, if I'm getting correct answer, I say the test is pass. If I have an incorrect answer, I say the test fails, so that I can then go and find out what is wrong with my RTL Verilog code. So I over the night I have developed something, and I could just let this thing run over the weekend for 2 days, and where it is just automatically logging, and I could come back and on the Monday and find out how good my tests were run and how many errors it has logged onto my file, my testing file. And that's how you should be creative to develop a test bed. So I asked ChatGPT for giving you a demonstration, an example. I wanted ChatGPT uh, to design a carry select adder, which it has done here. So a carry select adder is designed, and I want to do the testing of this using a golden model. And for the adder, golden model is very simple. It's only that you take numbers and add them with a carry in, and you have a sum and a carry. So I was really happy that it is very easy to because the golden model is can be easily designed, and we can easily verify the code. So that's once I instructed ChatGPT to do this. So ChatGPT has this test bed. So this is the test bench to check the functional verification of a carry select adder. And it says, okay, they are because now remember this is your device under test, and you are giving some input. Remember this arrow notation, and also remember that this has to be a reg, and this inside while this our reg or wire, depending upon which procedural block you're using assignment, but the output will always be wire. So you see here the output of this is the module, which is the carry select adder is carry select adder. And I want to validate this by having a golden model, which is just an adder, and giving the same input to this and getting the output and doing the comparison. And if it is correct, filing. If it is an error, filing. So it instantiated, it's this unit under test or device under test. This is my expected sum. This is the sum coming out of my, this is my C out. Okay, so it's totally, these are 17 bits. So the ChatGPT has just uh, defined a variable, which is a 17-bit variable. So I have my design instantiated like this. Then it has written a task. It says task check result begin. First, it is saying just add same inputs given to the model, generate an answer. So same input A plus B given to the device under the test here and getting an answer, and this model and getting an answer. Okay. And then only checking in this task check whether my sum concatenated with C out, making it a 17-bit number. If it is not equal to my expected sum, it means there is an error. So I say, oh, there is an error. So I say error when once a value of A, value of B, and C in expected was this, I got this. So I just want to make sure I just log this value. And else, if it is correct, I display this test passed. So this, if I at all, I want to also log the test that I passed in the same manner. I can just do that. If I don't want to write, I only want to write just how many tests I perform, because I may be performing millions of these tests, and I only log when there is an error. So this is the smartest way of so if you think about the UVM methodology, so you have a sequencer, and now you'll see a sequencer which is just generating all these numbers through, and that has another like a framework which you can just plug in here, but almost doing the same functionality. So the sequencer will just generate a sequence of test vectors, will through an interface, through a driver, will feed it to the device under the test, and then the output will bring the output back, and through a monitor where it will compare it with this, and then it will do the send it to the scoreboard that how many tests and what are the statistics, and also send into the regression analysis that how much I have covered the bits, and it's just 16-bit mean 2 raised to the power 16 into 2 raised to the power 16. So it's a lot of numbers that you have to generate. It may take forever. So you got to have a smarter ways of doing this. So this kind of a sequencer, it is saying initial begin. And again, ChatGPT has generated this. I have no role in it. But I really like the way it is being done. So it's saying generate from I0 to I less than 16, I is equal to I plus plus for 16. So you can have this 1600, 16,000, 16 million. You can change it to anything you want to. And here it is saying generate a random number, generate a random number, and generate a random number. Because the number has to be a 16-bit number, that's why it is dividing it by 2 raised to the power 16 minus 1, 2 raised to the power 16 minus 1. The maximum number it divides so that always the number which you get fits into 16 bits. So very smart. And again, here it is 2. So it is 2 raised to the power 1. Actually, 2 raised to the power 16, 2 raised to the power 16, 2 raised to the power 1. So whenever it comes, either it is 0 or 1, 0 or 1. So it will randomly generate Cn as well. And then it says wait for 5 minutes. Here it is calling the task check result. So it will call this task check result. Check result, what the check result will do, it'll pass these inputs to the device and to both of these and see the answer. And interesting is this, that there are always, we call them edge cases, which perhaps random number may fail to generate. So sometimes you should be smart enough to figure out the corner cases. Like corner cases are if both numbers are zeros, maximum positive number is a use case both for carry in 0, carry in 1, and just 1 and a 1 and carry in of 0. And this is the maximum negative number, minimum negative number, and maximum positive number with a carry in of 1. So you say just check results. So now you are ensuring that your adder, and this is the result I've gotten, pass, 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 pass. And it gives you the random number being generated, these. And from here onward, these are my corner cases. These are my corner cases. So you see, I really like it. Okay. So this is how it has actually achieved a very nice test bench, which has almost every element of how you write a good test bench. So you see that the tasks which has an expected, the model, and the statements where you are comparing these two, and randomly generating all kinds of inputs to your module with corner cases. So learning this would have taken somebody quite some time, but ChatGPT has generated all of this.